with an explanation just what is IRT?
IRT is item response theory. It's a theory what happens when a candidate meets an item, when he responds or she responds to an item. And the theory is a probability theory. It doesn't say what exactly will happen, it says what is likely to happen. Of course, when a candidate meets an item, the response to that item can be quite good, or it can be quite bad. It can be correct, or it can be incorrect. And the idea is that the likelihood, so the chance that that response will be correct, depends on the level of ability of the candidate. If the candidate has an ability which is close to the ability that is needed to solve the item, then of course the likelihood to solve that item becomes greater. And if the candidate has even more ability than is required, then the probability gets even larger. So that is the basic idea. And I want to show that in a simple graph. So if we think that we have development of ability along this line. So if a candidate is here, he is less able, and then the candidate becomes more and more able. You can think of the candidates ordered in ability. And now here on this axis, we project the probability that the answer will be either incorrect or correct. So we can have 0 probability, and we can have a probability of 1, which is the same as 100% chance of getting it right. Now let's first look at the probability of getting the item wrong. A candidate which has a very, very low ability has a very high chance of getting the item wrong. That's what you hope. And as the ability grows, the probability of getting the item wrong goes down until at some point it becomes almost negligible. Now let's look at the probability of getting an item correct. Of course, anywhere on this scale, the probability of getting the item wrong and the probability of getting the item right, there's nothing else outside. So the total must always add up to 100%. So if this is almost 1 here, the probability of getting it right must be 0 here. And then it gradually goes up. As that one goes down, this one goes up. And it crosses. And finally, when the candidate is very able, the chance of getting it right is 100%. And where these points cross is 50-50. 50%. But that's the idea of having an ability that to be able to be of a certain level of ability required for an item, you're looking to find the point where the likelihood that a candidate gets an item right is more than the probability that he gets it wrong. And that is not only at the item level. You can transform this also to the test level, or to any level system. So let's take a test first. You have a test of 50 items. If that test is measuring a certain level of ability, then the whole getting all the items correct on the test, of course, with ability grows. And in the beginning, the probability of getting all of them right is very low. And as a candidate grows in ability, the ability goes up. And finally, when he has a complete mastery, the probability is almost 1. Same applies to systems like the Council of Europe framework. If we think of the levels in the Council of Europe framework, there's a lot of misunderstanding about what those levels really mean. But using IRT, we get a better understanding of these levels. Think of level A1 and A2. Think of a candidate who's exactly at the borderline between A1 and A2. So we're saying he has mastered almost everything at A1, and he is starting to be of level A2. Within the concept of IRT, the point at which you say this person is starting to be at level A2 is where he has more chance to perform the task at A2 than he has not. So he is at the 50% level. And as he grows in that level, as he grows in level A2, he will move up and up in A2 and reach higher and higher probability of being able to do all the A2 tasks. But already, as he's growing in A2, he is also getting a higher probability in level B1. And at a certain point, his probability of getting tasks in B1 right reaches 50%. That is the point at which he moves into the next level. That is, this basic principle of probability is what is really the beauty of the system. Because we all know that when we're teaching candidates or pupils that there is no such thing as an A2 candidate and a B1 candidate separate from each other. It is a gradual growth. That is what is so beautifully expressed, I think, and modeled in the IRT theory.
But traditionally, John, we looked at difficulty of the item and the ability of the candidate separately.
Yes.
And IRT is bringing those together. What is the advantage of doing that?
The advantage of expressing the ability of the candidate and the difficulty of the item on the same scale, saying where the item and the candidate meet and are of equal value, there you get this 50% chance. The advantage of that is that we can also order our tasks on the same scale, and we can make a more insightful picture of what it means to be of a certain ability. Because if we order all the tasks on the scale from high to low, and we have a candidate who is at a certain point on the scale, then we know all these lower level tasks are going to be easy for the candidate, and those higher level tasks are going to be more difficult, and the candidate will have less chance of getting the correct answer there.
But I'm told this requires what is called unidimensionality. Can you help us understand that a little bit better?
Yes. The concept of unidimensionality is very often misunderstood even among the profession. When people think of unidimensionality, they think it should be only one single trait. But I can give an example where two traits still provide a unidimensional model. Say you are looking to buy a house and you want a nice large living room. And so you think, I really don't want any house, to consider any house with a living room smaller than 30 square meters. Okay, you look at all the advertisements and you see houses with 20 square meters, they're no good. 30 square meters, oh that's fine. 40 square meters, they're too expensive. So let's stick with this house with 30 square meters. You go to the house and you find out that the living room is half a meter wide and 60 meters long. Then you have been fooled. what has happened here? The broker has fooled you. He's not sticking to a general concept of what the format of living rooms is. If it's 30 square meters, you expect something 5 by 6. Some correspondence between the length and the width. And so you're speaking in a unidimensional model of the 20 square meter room and the 30 square meter room and the 40 square meter room. But this room, particular room, has violated the model. Same can happen in language testing. If we have items in a test which are measuring the ability of a candidate to gather some ideas from a text and to put them together and come to a evaluative response, then that is your underlying model of what is happening in the reading comprehension. If, on the other hand, some of the items all of a sudden are not following that model and they are measuring a different combination of language traits, then you will find you are in a problem. Mostly, however, what we see when items violate the concept of unidimensionality in language is that the items are in fact tapping some other skill. The most basic violations that we see are items which are requiring some background knowledge, which some candidates have and other candidates don't. And people are saying, well, the IRT model is very expensive because we have to look only for those items that fit the model. And then some people say, well, let's try and alter the model and use a 2-parameter model or a 3-parameter model. The problem with those models, however, is that you don't really know what you're doing. You don't know what the other parameter is. Let's take, for example, the discrimination parameter. People say, yeah, of course, items have different discrimination. Yeah. But what is that discrimination? Why is one item discriminating more than another? It can happen that items are discriminating differently because some additional variable is playing a role. Only those candidates which have a high knowledge in the language, for example, also know that the Eiffel Tower is in Paris. And there is a question which requires you to know the Eiffel Tower is in Paris. Well, it's very nice that you know that the Eiffel Tower is in Paris, but it's not language. And so we see that those items would have a higher discrimination because they are advantaging the higher level candidates. You can also see that items have a lower discrimination than other items. And mostly that is because they are not operationalizing the concept very well. They are kind of a mixed bag. If you look for items that are about of equal discrimination within a test, within a field test, within a trial test, and you select those items, you will notice that if you start out with 100 items and you pull out about 1/3 of the items which are not of the same dimension, and you remain with a much shorter test, that much shorter test, because it is more aligned to a single dimension, is going to have a higher reliability than the 100 items, which is contrary to the expectation, because mostly people think the more items you put in, the more reliable the test will be. Not if you're not having a pure measurement.
Well, if I may put this into the terms that people are going to find in the journals, you're talking about the Rasch model, is that right?
Yes.
Rather than the 2 or 3 parameter
Yes.
model. So for the Rasch model, what sort of numbers of candidates do you need before you can have some statistics for your estimations that are reliable?
In fact, you can think what kind of numbers you need at the same level as what numbers you need to trust your proportion correct number, your p-value or your facility value. Because it's all about, how many are in one group and how many are in the other group. And so if you have less than 100 candidates and you find a p-value of 0.5, 50% of the candidates have it correct. If you take 100 other candidates, it might easily be 0.6 or 0.4. The more candidates you have, of course, the more certain those percentages become. A rule of thumb for the Rush model, because you have only one parameter to estimate, is that you can work safely with about 200 candidates, and you'll be fine.
So if you've got the possibility of doing this kind of estimation, what kinds of tests that we haven't been able to do up to now, or before Rash model or before IRT, that become possible now?
I think it's more in terms of the information that we get out of tests and the interpretability of the results of tests that the advantage lies. We see in kind of context where IRT models are used now that people are trying to define their scales. We used to just have, put a lot of items to the candidate, and if the score is low, he's low ability, and if the score is high, he's high ability. Now we are actually scaling the task. We're saying the candidate is on this point on the scale, this is the type of task that the candidate can do. So you can think of tasks like they are described in the Council of Europe framework, writing a simple postcard, being able to do simple requests which are closely related to your own needs, right up to having complicated complaints about an airline ticket that wasn't delivered on time and that left you in the airport for too long, and so you have a whole complicated theory. And by describing those tasks at those levels, we get a much better picture of how language is developing.
What about the possibility of tailored testing, or the idea of being able to shorten the test by having the people take items at their level?
Yeah, that's another important characteristic of the IRT models, is that if you remember where we started out, we have a kind of a crossover point between the score of 0 on an item and the score of 1 on an item. That point is the most informative point, because if a candidate is very able and we provide him with a very easy task, then we don't really need to give the task to the candidate to have new information, because we already know that it is highly likely that the candidate will pass that task. Same at the opposite end of the scale. If we have a very difficult task and we give that to a beginner, then we know this is not going to be possible. So we're not getting new information about providing that task. The best information we get is if we try to match the level of the candidate. And so we try to get an item which is at the level of ability of the candidate. And of course, when you have different candidates, you would have different items. You need different items in your test. By honing in, by zooming in on the level of the candidate, we can get much more information out of this candidate item encounter, and thereby we can use less items than if we just throw a bag of items at the candidate. That can be implemented in sophisticated procedures on the computer, where if you don't know the level of the candidate beforehand, you try a few items on the candidate and you find out those items are easy. Okay, then you take the candidate up to a level with more difficult items. Or you find that those items are too difficult for the candidate and you go down and you try and find the level of the candidate. And the advantage of that method, which is called adaptive testing, is that you need much less items, so your candidates need less time. You can get the level of the candidate much quicker than if you just throw a bag of items at it.
Now there's computer programs available for doing this kind of calculation. And what's going on inside the black box? You know, we put our data in and we get these estimates, but what's the machine doing? Well, is there some way we can better understand that?
Yeah. What the machine is doing really is trying to find a level of certainty about the ability of the candidate. So if you say, if you program, or if you put a value in the program that you say, I want a reliability of 0.9 of my decision, I want no more error, not a larger error than say 2.5. You program the machine and the item, the candidate gets his set of items, goes up a level, goes down, and as the candidate moves through the test and gets items which are closer to the level of the candidate, the error around the estimate goes down until it reaches the level that you have set, that you are happy with. And then you have an estimate of the candidate with the certainty that you are looking for.
So the computer goes through a process of iterization until it reaches that
Yes.
preset, the point that you've said.
Yeah, the computer tries to find the level of the candidate by trying items, and if it goes fine, it's estimates that the candidate has more ability than needed for the item. If it goes wrong, then obviously the candidate has less ability than needed for the item. And by getting closer and closer to what the candidate is, the precision of the procedure will go up.
Now, when we're seeing reports of results of rash analyses, we sometimes see fit statistics. How does that fit into what we've been talking about so far?
Okay. I can get back to my example of renting a house. If you go and visit all these advertisements, and most of those 30 square meter rooms are 5 by 6, then all those will fit in your model. That is your model. You have a model that 30 square meters is for a room is something which is about equal in length and in width, and not half a meter by 60 meters. That room, which is a half a meter by 60 meters, is misfitting your model. Likewise, items that measure something else that is supposed to be in your model are going to misfit the model. I can give a good example of an item from the history that showed misfit. It's a speaking item, and there is a drawing. It's for a very low level candidate, so they speak based on some image, and it's a set of drawings about the candidate day in his life, and one of the pictures showed a person lying in bed and a little cloud above and a boy who's putting on clothes. The question put to the candidate is, talk about when you get up and which will you go and do. And the intention was, of course, I will get up when there was an alarm, when the alarm goes, and then I will get dressed. Boys performed beautifully on this item. They had no problem. But girls had a big problem. And why was that? Because they couldn't identify with the figure in the cloud. So for them, that item had a completely different meaning. So that item showed misfit. Because and this misfit was caused by bias. Bias against girls who felt confused having to imagine a boy getting dressed. But for the boy, it was himself getting dressed.
Well, thank you, John, very much. I think I have a better grasp of what this is all about now. Thank you.
Thank you.